Good afternoon, everybody. Thank you for attending this session on epidemiologic models. So we'll have three presentations. I suggest that we start right away with Yang Lu. Yang Lu, the floor is yours.
Okay, thank you very much. Thanks everyone. So today I'm going to talk about an extension of the SIR model. Sorry, I can't see my presentation on the screen. So this will be an SIR model with stochastic transition, and it's a joint work with Christian Gouilloux from Toronto and the University of Toulouse, and me myself from Concordia. Okay, so let me first give you some motivation. So we all know more or less the basic SIR model, and it has been really popular during the past year. And I think one of the most appealing features of this model is the fact that it allows to express some of the very important policy relevant notions, such as the R0 and as well as the existence of herd immunity. And at the same time, this model is very simple. It has just 2 or 3 parameters. So it's very mathematically tractable. But sometimes this kind of simplicity also comes with a price. And in particular, this model has the disadvantage that it is completely deterministic, so no uncertainty. And in particular, if you look at the key epidemiological measure R0, this measure is time invariant in the baseline model. But when you look at the data, usually when we have daily estimates of R0, and we usually observe that this time series is highly erratic. So this is the key issue that we would like to address in this paper. And we will do so by introducing what we call stochastic transmission. So we will allow the transmission ability of the virus to be time varying and stochastic. And this will help us to explain the huge variability of R0 that we observe in empirical data. And we're going to do this cleverly in the sense that the model that we propose will inherit some of the nice mathematical features of the standard SIR model. Okay, so we're going to introduce this stochastic version of the SIR in 2 steps. I'm going to first of all introduce what we call a semi-parametric SIR model, in which there will be a functional parameter. So this is not yet a stochastic version, which we will only introduce in, let's say, 5 to 10 minutes. So we will do this progressively. Okay, so as usual, you will have a population with 3 subgroups: S for susceptible, and then infected, recovered, etc. The proportion of these 3 subgroups will be denoted by XT, YT, and ZT. So these are the theoretical proportions. And then your semi-parametric SIR model will be defined by this differential system. So since XT, YT, and ZT sum up to 1, one of these 3 differential equations is in fact redundant. So you can see that you have 2 parameters. C is a scalar parameter. So this one also appears in the standard SIR model. Then you have a functional parameter A. So this function is positive. It is increasing, and it's defined on 0 and 1. And we require that A0 is equal to 0, which means that if there's no infected at the beginning, then there will be no infection. The initial condition that we are mostly interested would be the following. So Z0 is 0. So at the beginning, no recovered individual. And X0 is close to 1, whereas Y0 is is very small, is close to 0. So these are the fractions of 0 patients. Okay, so just a quick remark on the term A of xt in the previous equation. So this is a composite function. So basically it means that in our model, so this term measures the transmission speed of the virus, and this specific functional form roughly says that the way it changes according to time is through a specific clock, which is the epidemiological clock, which is measured by xt. So xt is the proportion of people at risk, and this proportion decreases over time because more and more people get infected. So this is a time change idea. So how does this semi-parametric model relate to the basic one? Well, if you take a linear specification for the functional parameter A, then you get the basic SIR model. Okay, but you can also think about other examples like power functions for any positive power exponent beta. So in fact, if you take the ratio between A of xt and xt, so this ratio is constant in the basic SIR model, but it's usually non-constant in the general specification. And this term has an interpretation of the instantaneous number of contacts that each infected person can have during a unit time. Okay, so for instance, if you have an increasing function, and given that, so if A of x over x is increasing x, and since xt is also decreasing in t, then you have an instantaneous number of contacts that is diminishing. So that is to say, it will become more and more difficult to infect new individuals. So this is what is known as mover-stayer phenomenon, or heterogeneity in the population. So in the sense that more frail population get infected first, so that the remaining one becomes more and more robust. Okay. So what are the major properties of the system under our model? Let's first look at the behavior at the beginning. So we are interested in the behavior of YT. So if YT is increasing at the beginning, then the pandemic will kick off. Otherwise, the pandemic will not start. So because of this first differential equation on this page, the behavior of YT is going to be determined by this multiplicative factor between the brackets. So you have two regimes, depending on whether A of 1 is larger or smaller than C. Okay, so you have a marginal case which corresponds to the case when A of 1 is equal to C. So this result can be regarded as an extension of the standard SIR model. And in fact, in that model, we know that this ratio between A1 and C is just what we call the R0. And we know that for that model, if R0 is smaller than 1, then we will not have a pandemic. Great. What about the behavior of the system for any values of t? So you have this proposition which provides you the closed form solution of xt in terms of the solution of some integral equation. So this is an extension of a recent result by Hackboy and others, which shows that in the baseline SIR model, we also have closed form solution. And this solution, this formula is quite nice because it allows us to avoid Euler type discretizations when we want to simulate from the differential equation. And so intuitively, when you use the Euler discretization, since the Euler method is based on time domain, on cutting the time, it's not going to work as well as it's not going to work so well compared to our integral solution, integral equation, which is based on which you can see is if you look at the right hand side of it, this equation, you can see that the integral is with respect to the epidemiological time. Okay. So in the paper, we actually document that if you use Euler type discretization, there can be really, really large approximation errors when some regularity conditions are not satisfied. Okay, and another important property of this integral equation is the fact that we're going to use this to check whether or not the population can reach herd immunity. So, so XT is, we know that XT is decreasing and it is positive, non-negative. So clearly this term will converge to some kind of limit, which we denote by x infinity. But this limit can be either 0 or positive. And if it's 0, it means that everyone will get infected sooner or later. If it's positive, then we will reach herd immunity. Okay? But right now, we don't know yet whether we will reach herd immunity. And if we do reach, we don't know yet whether we will reach the herd immunity in finite time or only at infinity. Okay? So these are the questions that will be answered by the following result. So this proposition gives us the condition for the existence of the herd immunity. So you have herd immunity if and only if this integral of 1 over a is larger than 1. Okay, and it also says that if you do reach herd immunity, it won't be very quickly. You're only going to reach that at infinity. Okay. On the other hand, if this condition is not satisfied, then you are going to all the population will become infected, and this will happen in finite time. Okay. So in other words, one of the findings of our model is the fact that you actually don't necessarily need to have a herd immunity. Okay. If you come back to the basic SIR model, in which A is a linear function, then we know that since 1 over U is not summable between 0 and 1, that inequality is going to be satisfied automatically. So in the basic SIR model, you will always reach herd immunity, and in that case, sorry, I forgot to mention that in case you have a herd immunity, this proposition also allows you to compute the final size of the population at risk, and that would just be given by the second equation, by the solution of this equation. And in the basic SIR model, this equation becomes the following one. So this equation with log. So what we can say, we can remark is the fact that in this model, in this basic SIR model, the final solution, the final size only depends on R0. And we just said before that R0 is also the measure which determines whether or not at the beginning the pandemic will kick off. So this means that the basic SIR model actually lacks flexibility because the same parameter R0 determines both the long-term and the short-term behavior of the pandemic. And when you have a semi-parametric version of the SIR model, you won't have this feature because in this case, the final size will depend on the integral of this functional parameter over the whole domain 0 and 1. So the final outcome will depend on the whole past history of the pandemic, which I think makes sense. Okay, so now we are done with the semi-parametric SIR model, and we are now able to announce the stochastic version. So just a little bit motivation. In the past, some people have tried to explain the fact that the daily observation of R0 is erratic simply by the fact that these proportions are not directly observable. And in fact, you only observe some empirical counterparts, which are obtained by, let's say, dividing the total number of infections by the size of the population. So you can have some kind of sampling error, which we call demographic uncertainty here. But I think over the years, the literature has come to the consensus that only taking into account this sampling error is not sufficient to explain the huge variability of the R0, the time series of R0. And that means we also have to take into account what we call environmental uncertainty. That is to say, the process of xt, yt, and zt are themselves stochastic. So this is the motivation of introducing a stochastic version of the SIR model. And so what we will do now is to introduce the environmental uncertainty first. Okay, so this will be done very easily by just replacing the functional parameter A in the previous model by a stochastic function. That is to say, a stochastic process. Okay, so the only conditions we impose on this stochastic process is that it's positive. It starts with it starts from 0 and it's increasing. So you have a couple of nice mathematical models that satisfy this kind of constraints. So for instance, you can think about Levy's subordinator. In the paper, we also provide other examples. So this is an example in which we have in which the stochastic function is a gamma process. So keeping in mind that so this is one simulation of the gamma process. So keeping in mind that in our example, in fact, when you do the simulation, you do backwise because you start with the initial state where xt is equal to x1 is equal x0 is equal to 1, and then as time goes on, xt diminish. So in other words, when you simulate this process, you start with its value at 1, and then you simulate backwards, and you make sure that this process ends at 0. Okay, so you can see here that with a gamma process, you can have a very erratic, very irregular pattern for the curve of the function A. This is what you obtain with that simulation in terms of the R0 expressed in epidemiological time. So in fact, you have two R0, depending on whether you would like to normalize it by the current size of the current size xt. So I think they are called basic R0 and effective R0. So you have their trajectories, simulated trajectories on this figure. So these are not yet what you observe in the data, because in order to observe that, you still have to do the time change from the epidemiological time to the calendar time. But you can already see that with this kind of stochastic process, you will be able to replicate the huge variability of R0 that you do observe in the data. Okay. All right. So these are some examples of simulations of some key epidemiological measures, such as the final size. So you can see that in this model, the final size is completely stochastic. You can have a final size that is very close to 1. That is to say, few people get infected, but at the same time, you can have a final size that is very small. So which correspond to the case where most of the people will become infected. You can also simulate other quantities like the size of the peak. So this one is very important for the management of the hospital system, for instance. Okay. Yeah. Then, so okay. So we just now we introduced environmental uncertainties in our model. We can also introduce demographic sampling uncertainties in our model. So in the paper, we developed such a framework. So this will be a kind of state space model in which at the bottom level, you have xt and yt that are stochastic processes. And then on top of that, you have further uncertainty because all the count variables will be stochastic, even if you condition on these underlying xt and yt. So just give you some illustration of some simulated counts for the number of infections on that given day in the 400th day of the pandemic, with a population of 50,000. So you can see that. So for this population, you can see that so on the left-hand side, you have the simulation with observation error, and on the right panel, you have the observation without. So you can see that most of the uncertainty come from the environmental uncertainty. Okay, so I think I can stop here. So this is a model of a new class of SIR model, which is still very tractable, but it's much more flexible than the basic one. And it is motivated by the fact that we want to better explain the large variability of some key epidemiological measures. Thank you.
Thank you. Thank you, Yang, for this presentation. I do have actually a question on the first model that you used. What is the interpretation of the beta parameter? So I believe, if I'm not wrong, that the alpha parameter can be interpreted as the average number of people that you would meet during a day or whatever. So that's there is an easy interpretation for alpha, but for the beta parameter, what would be the interpretation?
Alpha can be interpreted as the average number of contact at the beginning, because at the beginning u is equal to 1, and beta measures how this count number increases or decreases over time. Because what is important actually is not beta, but is beta minus 1, because we have said that the key measure is not the function a, but it's a of x divided by x. So so depending on the sign of beta minus 1, you can have increasing or decreasing number of contacts as time goes on. Yeah.
Okay. Thank you.
That is to say, the virus becomes less dangerous or more dangerous over time.
Okay. Or maybe it could reflect also a change in behavior from the people or something like this.
Yeah.
Or
Yeah.
many potential interpretations. Indeed.
Yeah.
Okay, thank you, Yang, for the presentation.
Thank you.
Now we can turn to the second presentation by Guillaume Rousselet.
Thank you. Can everyone hear me? Yep. So I'm waiting for the slides here, and then I'll be good to go. Very good. Thank you very much. So let me begin. Thank you very much for having the paper in the program. This is joint work with Jean-Paul, who is in the room currently, and Gustavo Schwenkler from Santa Clara. And what I want to talk about today is try to give you an assessment of how the U.S. Federal state and the U.S. states, individual states, have been doing through this pandemic, at least as of last year. So the question that we're going to try to tackle here is a fairly simple question, which is, what if any US state or the federal state had adopted different policies in terms of COVID-19 containment? And so Yang's presentation is a perfect segue into this presentation, because the model that we're going to try to play with is a stochastic SIR model with a multi-region. And so I'm going to consider each and every state in the US, actually. So what we're going to do is I have a state level model, and that we're going to aggregate from individual level. We're going to consider all states together and have like a large multivariate model, where we're going to have stochastic transmission rate and stochastic travel and commuting of people between the different states. Now, in terms of policies, because we're going to do counterfactuals here, we're going to ask the effectiveness of the different policies in terms of three types of policies. One is stay at home, the second is mask mandates, and the third one is interstate travel bans. We're aware that there were other kind of policies, but at the time that we completed our analysis, these were the main three that were actually implemented. And so we're going to throw that into our model, just estimate this with some sort of like large scale filtering estimation on all 50 different US states together. And so we're going to be able to extract a lot of information, such as the actual time series of the transmission rate, how it's evolved over time for each and every state. And the cool thing in our approach is that we don't really rely on data that could be questioned, or that is really where reliability is a key question here. We're just going to rely on death count observation and try to infer as much information as possible with these time series only. What are our counterfactual experiments going to be? Well, we're going to have 4 types of experiments and 2 branches here. So one is strict versus loose policy. Strict policy will be to maintain any of the 3 policies as long as another state does have it in place. Whereas loose policy is just going to be, well, no policy at all, and so let everybody run loose, essentially. And the second branch is we're going to consider these counterfactuals at the state level. So we're just going to keep everyone else equal, but say New York State is changing its policy. Or we're going to consider that at the federal level, which is, the federal state comes in and says, well, everybody needs to be doing the same thing, either like a strict policy or a loose policy. That's essentially the counterfactuals that we have. What are our empirical results here? The first one is that federal policies are actually effective. And our sample stops at September 30th last year, but we show that if the federal state had imposed strict federal policies for each and every local state, we would have reduced death by about 2/3. And federal mask mandates only actually just cut the number of deaths by half, and is able to basically suppress about 90,000 deaths if implemented on April 17th and ends in September 30th. At the state level, what we find is some of the states' policies could have been worse, a lot worse, and some of the states could have been a lot better, actually. So we find that if you suppress any kind of policy implemented by individual states, basically you find yourself with 1 million more more death, which is huge with respect to the actual number of deaths that we observed at September 30th, which was about 200,000. But we also find that the states that implemented no policies at all, basically Indiana, Nebraska, South Dakota, and Utah, with mask mandates alone could have prevented about 3/4 of their death, which is kind of huge. In the end, our study shows that travel bans have pretty much low impact, and they're not extremely efficient in achieving containment of death in a state. All right. This is the related literature, but I have no time to talk about this, so let me go directly to the model. So I'm going to go through the model quite fast because we've had a glimpse through it through Yang's presentation. But basically, let me detail a bit what's going on for just a single area. So we have 2 days here, date T and T+1, and we have 4 populations: susceptibles, infected, recovered, and dead. When you're a susceptible person, either you stay as you are with probability 1 minus alpha t, or you become infected with probability alpha t. Note that this alpha moved through time, which we're going to be exploiting this stochastic feature of this stochastic transmission rate. If you're infected, you can either stay infected, become recovered with probability gamma, or become dead with probability delta, essentially. And then if you're recovered, you stay recovered, there's no reinfection. And if you're dead, obviously you stay dead. And then, the model just propagates through different points in time. So from day T+1, you have the same thing, except that now what's changed is the transmission probability alpha t has changed to alpha T+1, and it evolves through time. Okay, so we take that basic model, put it into mathematics, essentially. Susceptibles evolve according to, you're susceptible and some people become infected. What's really the most important here is the evolution of the infected people, which, it's the last number of infected people minus the people who become recovered minus the people who become dead. And then the new number of infected people, it basically follows this Poisson distribution, where the intensity is in red, and this is the average number of new infected people. The IT, ST over P, P being the population of the state, is essentially the basic SIR form. Well, beta T is really what changes with respect to a standard SIR model, and beta T is going to play the role of our stochastic transmission rate here. And so we're going to try to estimate that beta T from the data. But the key point here is the more infected people they are, the larger the chance of being infected. The more susceptible people they are, the more chances of someone getting infected. And this gets all scaled by that transmission rate beta T. Now, this was for a single state. We're just going to throw that into many states. And here for illustration, I have just 4 states to try to show you how that plays a role in our specification. So the idea is that all populations can move across states. And so by moving, they either commute, which means they stay for part of a day, or they travel, which means they stay longer term, essentially. So randomly, we pick some people in state A, and they're going to move to state B, state D, or state C. Here in that example, there's no people moving to state C. But here, the red people move to state B, the blue people move to state D. And then among these people, some of them are infected, some of them are susceptibles, recovered. They've been drawn from the population. And the infected people here are in yellow, and they're basically going to contribute to the infection rates of state B and state D instead of state A. So basically, the transmission in state A is going to be a little bit smaller, but the transmission in state B and D is going to be higher just because you bumped up the number of infected people and susceptibles in these states. So now what happens to our nice equations? Well, here the first equation, if there's no interstate commuting or travel flows, you basically end up with the same Poisson distribution, but only there's a J index here that plays the role of we're looking at state J. But when you're introducing the state flow, you replace the basic number of infected people in that state by infected plus the infected people that have been traveling to that state plus the infected people that have been commuting to that state. And then the same thing goes for the number of susceptible peoples that has been bumped up by the number of people that actually came to that state. So it looks a little bit more complicated, but it's nothing more than just taking into account the movements of populations between the different states. And since we assume commuting is just part of the day, we just multiply this by a number that's smaller than 1, which is the fraction of the day that's spent in the state that you work at, essentially, when you commute. Now, these numbers are all random, and we draw them according to binomial distributions where we have matrices of movements across populations, so we're able to simulate the flows, essentially, or just draw that from a particular distribution. So now the core of our representation is about the policies. And as I mentioned earlier, we have 3 types of policies. We have masks, stay-at-home, and travel bans. What we choose to do with respect to these policies is model each and every one of them as binary variables. And so these are the thetas here that you see. And these thetas can take 2 values. They can either be 1 when no policies are implemented, or they can play the role of a reduction factor, and so be a number below 1, essentially. And so what these policy dummies are going to do is play a role on the effective transmission rate, and so they're going to multiply what we call a basic transmission rate. So if we look at the table on the bottom of the slide, we have the transmission rate, which is basically the beta I was talking about before, which is equal to the basic transmission rate multiplied by the policy dummies. And so when the policy is activated, basically that transmission rate is going to be multiplied by the dummy, and so it's going to decrease by an amount, by a proportion which is equal to that low value. So what do we have? Where do these policies play a role? Well, mask and stay-at-homes are going to decrease the transmission rate in a state. And where they're both implemented, they both decrease this transmission rate. Stay-at-home is going to have an impact as well on the commuting probability. When stay-at-home order is implemented, you basically commute less, and so that reduces the probability that you're going to another state for part of your day. When stay-at-home and travel bans or either one of these policies are implemented, basically you're reducing the probability to travel to another state. And so all of these probabilities are shrunk down by the amount given by these policy dummies. And so we're going to see that the travel ban reduces that probability to travel quite dramatically, for instance, in the calibration. So I'm going to not detail everything. There's a slide after that that's going to give you a little bit more insights of what's being taken. So, some maybe parameters that I want to comment upon is this gamma, which is the probability to recover, is about 1/14. So we sort of mentioned that the recovery takes about 14 days to happen. We play a little bit with that number in the sensitivity analysis. That doesn't change too much. We have a fertility rate of 0.6%, and we translate that per day, essentially. And we say that an average worker spends, 8 hours of its time working in a neighbor state. So this is, gives us the proportion of people staying in commute. And then the important part is the reduction factors, which is basically masks reduced the transmission rate by essentially 42%. Stay-at-home reduces the transmission rate and all the other commuting and traveling parts by essentially 36%, and travel ban reduces movement by 90%. You might ask, well, where do these numbers come from? For masks, it's essentially the typical mask filter out 85% of particles, and then we divide it by 2 because we're saying there's some compliance problems when you implement these things. And we take data from the Health Metrics and Evaluation Institute. Travel ban and stay at home are measured from reductions in inflows and outflows, and we take data from the Bureau of Transportation Statistics and cell phone mobility to do that. And again, if you're not happy with the numbers, in the paper we have some sort of robustness and sensitivity analysis of these different calibrated values. Very quickly, we estimate them all with Kalman filter-based estimation. And the thing that I want to point out here is we're doing a joint estimation for all states. And so we have 51 states, so because we include Puerto Rico, I think. So we have the 50 regular states plus one. And so at the end of the day, what we need to filter out is the susceptible, infected, recovered, and dead population plus the basic transmission rate here. And so that amounts to essentially 255 series that we need to back out from our input data. We have two kinds of input data. We have the policy dummies that we sort of take from other data sources that I mentioned before. And we have the death counts that we take from the Johns Hopkins University website, which is the standard for the death counts. We sort of like throw that into a nonlinear Kalman filter, estimate some parameters, and then filter out the different series. I should mention that our data is daily. We start in February 22nd last year, stop in September 30th last year, and our death data is seasonally adjusted weekly to avoid the effect of over/under reporting per week. Okay, what are the typical outputs of the MUL? Well, this is the sort of things that you can find. This is the effective reproduction numbers state by state. And then we aggregate this over the US. So it looks like they're all very much correlated, which is true, and this is something that we get out of the MUL. They're fairly correlated, but you see some state-by-state differences. I should mention the blue line is essentially the reproduction number of one, above which you have a virus that is spreading, below which you have a virus that is shrinking. So if you look at Alaska, for example, which is the second plot here, at the end of the sample, the reproduction number was about 2, whereas, say, in Colorado, which is the 6th to the right, the reproduction number was about 1. So you still see some differences in the reproduction number of each and every state, and you can actually get that measure real time when you're doing the estimation, which I think is not the focus here, but it's kind of a nice byproduct of the MUL that we have here. So a couple of outputs that we actually like from that MUL as well. You can aggregate these reproduction rates to get the aggregate US reproduction number. And you can see the spikes in July and September. So that reproduction rate is basically going to soak up anything related to, I don't know, change in social activities, density of the populations, or where people move. That's not captured by our travel variables, for example. All these sort of things sort of give you a sort of sponge variable that allows to summarize the state of the virus at any point in time. What's kind of interesting as well is the number of infections through time. The blue line here is what the data from Johns Hopkins University measures, and the red line is what we measure. This is in log scale. And so there's a large difference in the beginning of the sample, and that difference reduces and reduces. And now, as of September last year, we were about 5 times the actual number of infections measured from the MUL was about 5 times bigger than the one that's reported in the data. So you can actually sort of correct for the slight misreporting that you see in official numbers. Now let me move to counterfactuals. So I presented before the loose and the strict scenarios. Here's a couple of details, but for the interest of time, let me just move to the actual results here. So this is what I think is one of the most important plot of our paper. This shows the evolution of the number of deaths in the data as well as in the counterfactual scenarios. So the black line here is the number of dead people that you see in the data. And you can see clearly that in the summer there was a pickup here, which is the second wave was starting in some of the states in the US. And at the end of the sample, we're at about 200,000 deaths. Red line is counterfactual. If we implemented masks as early as 17th of April, you can see that you're kind of like slowing down out the first wave, and then you take a little kick at the second wave, but you're basically saving about 80 to 90,000 lives. So it's fairly effective. Now put a stay at home, and the stay at home is works earlier because it starts March 20th, and then you get that gray line, which basically allows you to avoid 2/3 of the death, and you're about 70,000 death at the end of the sample. So it works a little bit better just because you started earlier. Put all policies in place when the first policy was implemented, you get that beige line, so you get an extra kick of about 20,000 number of people that you were able to save. And now think about the economic cost of these different policies. Essentially, stay at home is much more costly because essentially you're asking people to stay at home, whereas masks allows you to function as before. And think about putting masks in place as early as the 20th of March. And so you get that red dashed line just because you're essentially preventing a lot of death from happening earlier on, and you sort of like smooth out the second wave as well because of the implementation of mask policy. Let me skip this slide and just go to travel ban results. So here you have travel ban, the number of deaths that could have been prevented by travel bans in yellow on the right column here. It's about 5,000. It's not big compared to the other policies, just because for travel bans to work, you have to implement them very early. Otherwise, they just merely redistribute people across state lines. Now, about the implemented these policies in states. Some policies actually worked. Some states could have been better. Here we show that New York and Vermont basically could, by being stricter, could have only prevented 20% of their death, while some people could have prevented about 100% of their death, like Texas and Arkansas. And then let me just focus on this. If just a single state implemented these different policies at the same time, we show that states that were pretty loose, like Florida and Texas, on the left-hand side at the bottom of this plot, could have prevented about 30,000 different 30,000 deaths, which is quite big just for two states to be acting on this. So states could have done much better. We show also that states could have done worse by just computing the same counterfactual by letting everybody run loose. And then we have a bunch of other results in the paper, and I'm pretty much over time, so I'll stop there. Thank you very much.
Okay, thank you, Guillaume. You're out of time now, so thank you for the presentation. There was one question that I received just after the presentation of Young. But I guess it applies also here to this to this second presentation. So maybe that both Guillaume and Young can address it if possible. So the question was about the fact that the approach here does not integrate population reaction to the risk. So that's true that these models are somehow mechanical, maybe. So I don't know, Guillaume, you want to address this point?
So that's, first of all, that's a very good point. There's no endogenous reaction of the population to either the policies or the state that the virus is taken. There's been some papers that have shown that there's actually, even if you don't implement policies, the fact that people see the numbers and that the infections go through make them change their habits and just stay at home more, even if there's no stay-at-home policy. So that's not in the model per se. Now, what I might add is, as I said, the transmission rates, when you put them as a stochastic equation, they sort of pick up whatever you leave out of the model. So it's a bit underwhelming in some sense, because you're not really giving a justification of why these things are moving over time. But at the end of the day, if there's a significant change in habits in the population, basically that's going to appear in the transmission rate. You're just not going to be able to explain why. But that's the way I understand it in these reduced form models. I don't know whether, Yang, you want to add something there to this point.
I agree with I agree with Guillaume that that one of the important weakness of this kind of model is that it's very difficult to integrate some kind of either endogenous change of reaction by people, or even exogenous policy level change. Well, Guillaume's model has an example of having exogenous policy, but in general, yes, it's very difficult to say that that the uncertainty are due to change of policy, change of people's behavior or government policy, etc., etc. At least in our SIR type model, yeah.
Okay, thank you. So I guess now it's time to switch to the third presentation of the session. So Antoine Diogbenou is going to make this third presentation. So Antoine, you can start now. Thank you.
So first of all, I would like to thank the organizer for giving me this opportunity to talk about my research. So I'm trying to connect to the platform. Okay, that's fine. Now I think I'm getting. So so this is a joint work with Christian Guerrero from University of Toronto, Touro School of Economics, and also my colleagues Joan Jaziak, Paul Risson from York University, and one of our former PhD students who is now working as a risk modeler in a bank. So today I'm going to talk about a transition model for coronavirus management. So I kind of see my work as kind of complementary to Yang and Guillaume's presentation. So as they mentioned already, the basic epidemiological model usually contain 4 individual states. We have the state X of susceptible individual who are healthy, not yet immunized. And we have the state I of infected individual who have not yet recovered. Now, we can also think of whenever someone is infected, either he's gonna recover and move to the state we're gonna call R, or he's gonna die and then move to state D. So in this model have been developed back in the late 30s after the Spanish flu, and has been used in many other contexts, as you can see in the previous presentation. So this basic model can be viewed as a causal scheme where we have a chain with at least 2 episodes. The first episode is the one which where we have we have to look at the propagation of the phase of the disease, the detection of infected individuals, and this has been widely discussed, like what we saw in the previous presentation. We have the second phase, which concerns the monitoring of the disease, and we are mainly interested in this second phase. That is why I think of my work as complementary to what they just mentioned. So our interest here is to propose a transition model which can be used to analyze individual history. So this is going to be particularly useful, as you're going to see from the result we're going to present, that's going to be useful to manage the healthcare system, and that's going to become clear soon. So first of all, we are kind of proposing a discrete time dynamic transition model, which is based on individual history. So this is kind of different from the usual shared model, where we consider usually aggregate data. So we're going to be looking at individual history here, which I think is an advantage. But another advantage of the model is that we're gonna the kind of model we're gonna allow the inclusion of individual and time-specific explanatory variables. So, for example, we'll be able to include the duration, because we think that the time you spent in a given state are gonna explain what we mean by state here. That's gonna affect your transition to other states. So we divide, in order to have those states, we're going to divide the different the phase of medical care into phase of increasing intensity. So we're going to call each of them states. We're going to have different states. I'm going to list the states soon, but this is going to depend on the severities of the symptoms. So at the end, we're going to trace out the daily transition of patients through the healthcare system, and we're going to try to address some of the issue we have. Actually, one of the issues you have with dealing with individual data is that you have to address some reporting issue, and we're going to propose some techniques to handle those difficulties. So the modeling approach we have, we think it is providing reasonably accurate results, and those results I'm going to show them to you during my presentation. So the kind of data we have, let me show you what our data look like. So we have like more than at that time of the pandemic, when we started working on this, it was we had the data around May 7th, 2020. So it was the early phase of the pandemics, and we have this kind of data. So we have more than 18,000 people who were diagnosed with COVID-19. The kind of data we have in a row in our Excel file, you have all these individuals, but we have column with what happened at the given date, like when they moved to a different state and so on and so forth. For example, the first guy there, he was reported officially as a COVID case on March 29. And he had to go to emergency room on March 26, return to hospital on April 3rd. He was under ventilation on April 6th, and until April 23rd, and not yet recovered at May 5th, which was the last day in our data at that time. So, for example, the third guy there, this was a case reported on April 2nd. He was hospitalized on March 31st, and he went to the ICU in April 2nd and died sadly on April 3rd. So these are the kind of information we had, right? And you have all this column, and we have to put this in terms of data. And in order to do that, we assume there are some states, and this is what we consider as the state. So we have, we're going to consider mainly, we're going to have 9 states, but we're going to be dealing mostly with 8. So the state 0 is the state of undiagnosed individuals. So whenever someone is diagnosed, he's going to be in one of the 8 other states we're going to consider. Our analysis is going to be conditional on the fact that you guys has already been diagnosed. And we're going to look at what happened when he's diagnosed, like what are the different steps which you're going to follow. So what can happen is that someone who is diagnosed can be the health authority can decide, okay, if you have mild symptom, usually these guys are usually domiciliate, which we're gonna call state D. So you can be isolated in that case. So, but you are diagnosed. If you are diagnosed, sometimes people tend to go to emergency room. According to our data, most of the people who go to emergency room, like they only spend like 1 day maximum. Most of the people, and then we're gonna call this ER. Some people are hospitalized, and because we have some people who were hospitalized, who were already in the hospital, and there were some issues that, so we just kind of define hospitalization due to COVID to make clear that what we're looking for is COVID. So this is gonna be state H. We're gonna whenever sometimes some of the people, depending on the severity of the symptom, you might be admitted to intensive care units. And if it become more difficult, then some people are ventilated. So ventilation means that you are using kind of respirator. There are different type of respirator which help you to breathe when you have severe symptoms. Sometimes you have intubation. This is more like there is more dependency to the ventilation. So, and then in that kind of time, they have to use a tube and put it. And this is also help the airway to kind of relax a little bit to reduce the pressure. So beyond that, we also consider the state of recovery or deceased, which was also discussed in the other cell model. So one of the things I want to mention here is that the kind of data we have, like you're gonna see sometimes some people who were hospitalized, but it's mentioned that during the same period they were also at the intensive care unit. So it makes sense, right? Someone who is at the intensive care unit is hospitalized. But to deal with this issue, we're gonna say that, okay, we want states to be disjoint events, right? So we're gonna say that someone who is hospitalized, we're gonna consider as hospitalized someone who is who during the specific period we are looking at, if there is someone who hasn't been in an intensive care unit receiving ventilation or intubation, we're going to consider him as hospitalized. So if you move forward, someone who is, we're gonna consider someone to be at intensive care unit. If the guy haven't received any form of ventilation yet, and also haven't been intubated, and we're gonna consider someone to be ventilated if he hasn't received any form of intubation, and then the last state is intubation. So that's how we discretize things. Now, I just want to mention that so for the ease of exposition, I will not be putting the T with stars and V with star. We just drop them out in the following part of my presentation. So given this definition of the states, I just want to mention, just to help you see exactly what we have as data. So we are using in our study data from the Public Health Ontario as data we obtained as of March 7, 2020. So we had more than 18,000, to be precise, 18,722 individuals diagnosed in the data we had, and then we observed them. We observed the daily records from the period of January 23rd to May 5th. Just want to make sure that you see there were a lot of variety in terms of hospitalization here. So we had more than 2,000 people who attended at least one of the health, one of the medical stage, intensive care unit, hospitalization, and so on. The most frequent stage here is actually hospitalization. So just to give you some idea of where we are, so the population of Canada is around 35 million. Toronto, Ontario first, which is one of the largest provinces in Canada, have approximately 14.5 million population, which is approximately 38% of the overall population. So Toronto is kind of a major city in Ontario. So Ontario is one of the largest provinces in Canada, but Toronto is also one of the important city in Canada. So we're gonna also look at some point at what happened, for example, in Toronto compared to the neighborhood of Toronto, those kind of things. That's what we are looking at. So given this data set, if we just want to assume that we have something standard, we have an homogeneous Markov chain, we can estimate some probability of transition. So this table you have here, actually, the rows are the states from which a patient are moving from. As I mentioned at the beginning, we are working conditional the fact that the guy has been diagnosed. So we're gonna look at first, when someone is diagnosed, he can be isolated, what we call domicilied, or he can be at emergency room at some point in the time. He might be hospitalized, intensive care unit, ventilation, recovered, or dead. So deceased. So you can see the first 6 row like an input in a production process, right? Someone who is diagnosed can be somewhere there. So these are gonna be the inputs in our production process, but the output is gonna be like recovery or death. So some might recover, some might die. So just to see a little bit of intuition of what we are showing here, just help us to see how we should write our model, right? Transition. So you can see, for example, that in our data, there is no one moving from emergency room to intensive care, ventilation, intubation. There is no one moving from intubation, ventilation, intubation, ventilation, intensive care unit to emergency room. We have 0 probability. We just want to give some explanation, and which gonna give you some intuition on how we're gonna extend this model, Modius Markov chain. Just want to say, for example, if you look at the guys who are hospitalized, which is you look at the row H. If you look at the intersection with the colon dead, DE, you're gonna see that there we have probability. What we have there is that for someone who is hospitalized, the probability that this guy is gonna die, the 2.9% approximately, regardless of how long the guy has spent in state hospitalization. Right? We're gonna kind of extend this and develop a new model, which is a model which can allow for duration dependence. So we're gonna, those transition probability, we're gonna allow them to depend on individuals' specific characteristic, and and also the time. So we're gonna index it with int. So we're gonna have an 8x8 transition matrix for each int. So we're gonna have 8 row, 8 column. J here gonna indicate the state the individual is moving from. K gonna indicate the landed state. So interestingly, here we can model row by row, right? If you move from somewhere, what is the probability that you end up in one of the other 8 states? So we're gonna model each row by assuming that we have a multinomial logit model. If you have a multinomial logit model, you just use it mostly because it is attractive and easy to manipulate in this context. Some other model can be used as well, like Probit, and work well. So here, if you look at each row, we can actually, given that we are using logit, we can make it depend on some variable, explanatory variable. We are interested in particularly here in duration dependence. So we're gonna allow the duration, the time of sojourns of individual in each state, the time the guy has already spent in a state as an explanatory variable. And we're gonna look at on the coming slide, I'm gonna show you how this affects the transition to other states. So because we have actually many of these, right? And for the sake of time, I want to be able to present the result for all the states. I just choose one, which is intubation. I think many people are scared about intubation. What happened when you are intubated? Some people didn't want to be intubated. Those kind of things. It's sad, but yeah. But I have to analyze that, and I'm going to show you, for example, what happens when someone is transiting from intubation. In order to present the result, I'm going to show you for approximately 15 days, if you spend some time, how that's going to affect the transition to other states from time. We did the same thing for all the other states, but I will be presenting only one and show you some of the conclusion we draw based on this analysis. So on this graph here, we have many panels. So each of them are the transition to, for example, the first one, when you look at the left top, you have transition from intubation to domiciliate. For example, if you look at the bottom right, you're gonna see transition from intubation to death. So the x-axis here represents the duration. We just look at for 2 weeks, or approximately 50 weeks, 15 days, how individual move. So the y-axis are the probabilities. So you can see, for example, there are a few things we can see from here, which is that if you look at the right bottom, which is the transition to death, this show that the more you spend time in intubation, the higher the probability of death, right? If you look at, but we can see also that if you look at the left at the bottom, you're gonna see transition to intubation, and from intubation to intubation, which means that people are more likely to stay. If you are already there, you are more likely to stay. One thing we can also do, actually, with the displayed probability we did in the paper, is that we use this probability to compute. We compute what is the expected duration someone gonna stay, given that he is already there. Like, for example, if you are at day 1, what is the expected duration you're gonna stay? And this can be computed by taking 1 over 1 minus the probability of staying at intubation. For example, here, when you look at after day 1, for transition of intubation to intubation, day 1, we have approximately 0.6 probability. If you compute that, you're gonna find that the expected duration someone like that gonna spend is 2.5 days. If you move to, for example, 10 days, the expected duration gonna be approximately 5 days. So that means that actually the expected duration, the more you spend time in intubation, the more likely things become more difficult. Now, if you look at in terms of probabilities, in terms of probability, we can also compute the probability of quitting to, for example, another state. For example, after day 1, we can compute the probability to move to death. That's going to be the probability of moving to death divided by 1 minus the probability of staying intubated. That's going to give us the probability conditional on quitting. So we can see, for example, that after day 1, the probability of quitting to death from intubation is actually something around 0.05. From after 10 days, it becomes 0.15. We have encountered in some way the mover stayer phenomenon, which is that those that have less severe symptoms, they're gonna move sooner compared to those who have severe symptoms. Now, we also did something similar for the other states, but some of the things we did was to compare, for example, Toronto, which is the major city in Canada, even in Ontario, but also in Canada. We compare it to what is happening in the Greater Toronto area. We have approximately, in terms of number of cases, the same number of cases. At that time, for example, we have something like 5,900 for each of the two areas. So in the great, so the dark solid line is for one for Toronto, and the one is the one for the Greater Toronto area. So we did some kind of analysis we did before, the same kind of thing we did it here. So something I want to mention, for example, if you look at the death part, transition from intubation to death, it appears here that there is individuals. So we have the same pattern as the one we saw before. The pattern looks very similar, except that there are differences in magnitude. For example, someone is more likely here to die over time in Toronto. When we look at transition from intubation, people are more likely to die. But we can also see that people actually move from, they are more likely to die in Toronto compared to the GTA area. But one of the things also we can see here that people move more slowly from intubation people move more slowly in intubation in the GTA area compared to Toronto. So that people are more likely, for example, look at T2 ECU, T2 ventilation. So actually, a comparison with some of the other results we have is, for example, when you move from we move from D, which is for domicilied. We saw that, for example, people are treated sooner in Toronto compared to other area, and there were actually less deaths for people who are isolated in Toronto compared to the GTA area. So we cannot say that actually one is doing better than the other one, but the kind of recommendation we can say to policymakers is that they kind of harmonize because there is a difference in practice across regions. They can harmonize this, and also we also saw that there were difference in terms of reporting of the data. So maybe that this can also be due to that, and policymakers might want to take into account and see how they can harmonize things, and particularly in this early phase of the pandemic. We also tried to see how we can do some prediction. So in order to illustrate how good our procedure is, we are comparing our fitted value, our fitted count of individual in different states, medical state more precisely. We compare that to the actual data we have. One of the things, as I mentioned at the beginning, we have to deal with is the problem we have with data. For example, we find out that there is a lag in reporting of people in the different medical stage. So it is difficult to do kind of prediction in this context. We propose a technique which can be used to handle this. We are kind of doing our prediction based on newly detected individuals. That is a little bit more accurate. So once you have an individual which is detected, we're going to look at different cohorts. So think of, you want to do prediction for a given time T, you're going to look backward and think of all the people who have been detected before. And for each individual detected at each day, it's going to be a new cohort. So we're going to, for this cohort of people at a given date before, we're going to apply the assignment vector, which is the probability of transiting to any of the other state estimated from this data. So we could do that for each date. And once we have this individuals that are in the given different state, we apply the transition matrix P in order to predict future counts. And then we predict them up to time T, and then we sum of people from the different cohorts at time T. By doing this, we have a better prediction of the future count. For example, if you look at the right side, so this is estimated count in terms of the days. So if you look at the right side, these are the counts. You're going to see something which will look like a peak, but this is not a peak in the real data. It is mostly around 80. After 80, we had a lag in reporting. So there were no decrease in people hospitalized. And our proposal is, our method proposed actually is helping to predict upwards actually the number of people in the different states, emergency room, hospitalized, ventilation, and so on. So the last, so here we are doing better for the count, for the death rate, because there is no kind of issue there. So to conclude, we propose this transition model, and we think that we are dealing better with some of the issue we have in the data, and this procedure can be extended in different directions. We look at that in different paper. I think I'm out of time, so I'm gonna stop here.
Okay, thank you, Antoine, for the presentation. So I do have a question. So you have this transition probability matrix, and so if I understand correctly, once you have if you just consider that this is the model, then the transition probabilities that do not depend on the duration, right?
Yes.
And then after you say that you extend the model in order to take into account the duration, but then so what is the so you estimate something at that stage? So that's to say, apparently you have shown very smooth transition probabilities. So I suppose that you posit some parametric functions for these things, and that's what you estimate, right?
Yes, actually, maybe I wasn't clear. Okay, actually, assume that we have a logit, right? Multi-number logit. So, so we can, for each row, we can, individual transiting from a given state, we can look at the probability of transiting into many other states, like the 8 other states. So we assume that there is a logit, multi-number logit. It can help us to model this. So we make this multi-number logit depending on duration. So we have parameters. We have a constant, we have a slope associated with this duration, exactly, and we have to estimate this. I'm not sure that here, but we estimate the parameters. The parameters themselves are not directly interpretable, but we can interpret ratio of the probabilities. We can interpret conditional probability. This type of thing.
Okay, so the probabilities that you estimate in the end are like combinations of logit functions, right? Because I guess
Yes,
to make sure that the sum of the probabilities is equal to 1, I guess you have to
exactly. We have to take all this into account. So we have to have, so we specify it row by row. So the first row we can estimate something different from the second row. So for example, for the states where we have 0 probability from the Markov chain, we are not including, we are assuming directly that it is 0. But now where we have non-zero probability, for example, for the death rate, we are not making the death rate depend on the duration. That's something I have not said, but it's in the paper. But now for all the other states, like we are making them depend on duration so that we can know that, for example, because people only spend 1 day in with emergency room, we don't make that depend on duration. But for the other transition, we are making them depend on duration, and we have parameter we have to estimate. We have standard error for these parameters. All these things are in the paper.
Okay, thank you,
Antoine.
So I guess thank you. I guess we're a bit late now, so I suppose that we have to stop this session now. So thank you very much for your participation to this session, and I think that in the program now there is the poster session. Okay, thank you very much.
Thank you.
Bye.
Thank you.
you.